In the year 1929, the astronomer Edwin Hubble made a discovery that forever changed our understanding of the cosmos. While peering through the 100-inch Hooker telescope at Mount Wilson Observatory, he observed that distant galaxies were moving away from us, and the further they were, the faster they receded. This simple observation led to a profound conclusion. The universe is expanding. And if the universe is expanding, then winding the cosmic clock backwards means that at some point in the distant past, everything must have been compressed into an incredibly hot, dense state. A singular point from which everything we see today, every star, planet, galaxy, and even the fabric of space-time itself, emerged in an event we now call the Big Bang. But this realization brings with it a natural question that has puzzled philosophers and scientists alike. What came before? Did the universe have a beginning, or has it always existed in some form? For decades, the standard answer was that time itself began at the Big Bang, making the question of before meaningless, like asking what's north of the North Pole. And yet, as our tools of observation grow more sophisticated and our mathematical models more refined, scientists are finding tantalizing clues that there may have been something before the Big Bang after all. A before that defies our conventional understanding of time and space, but a before nonetheless. The question of the universe's origin is not merely academic. It strikes at the heart of our existence. We are, after all, collections of atoms that were forged in the hearts of dying stars, on a planet orbiting an unremarkable star in an ordinary galaxy. We are the universe examining itself, and our curiosity about our origins is perhaps the most profound expression of cosmic self-awareness. As Carl Sagan once said, "We are a way for the cosmos to know itself." And so, the quest to understand the universe's beginning is, in many ways, a quest to understand ourselves. The story of the universe's origin is our origin story too. But to understand the universe's possible before, we first need to understand its beginning as we currently conceive it. The Big Bang theory is one of the most successful scientific theories ever developed, supported by multiple lines of evidence, from the cosmic microwave background radiation to the abundances of light elements in the universe. However, it's important to clarify what the Big Bang theory actually states. Contrary to popular belief, the Big Bang theory doesn't claim that the universe began as a point-like explosion in pre-existing space. Rather, it describes how the universe expanded from an extremely hot, dense state. The earliest moment that the theory can reliably describe is approximately 10 centimeters water feet to 43 seconds after the initial expansion began, a time known as the Planck epoch. Before this vanishingly small fraction of a second, our current physics breaks down, unable to reconcile quantum mechanics with Einstein's theory of general relativity. And so there exists a gap in our understanding, a cosmic blind spot that has fueled speculation and driven theoretical physicists to develop increasingly sophisticated mathematical models. In this scientific frontier, three main approaches have emerged to peer beyond the Big Bang's veil: inflation theory, string theory, and its offshoot of the cyclic universe, and loop quantum cosmology. Each offers a different perspective on what might have preceded our observable universe, and each comes with its own set of predictions and problems. Let's start with inflation theory, which was first proposed by physicist Alan Guth in 1980. Inflation theory doesn't actually describe what came before the Big Bang, but rather what happened immediately after it. According to this theory, the very early universe underwent a period of exponential expansion, doubling in size every tiny fraction of a second. This expansion was driven by a hypothetical field, the inflaton field, that filled all of space with an enormous amount of energy. As the inflaton field decayed, it released its energy, filling the universe with matter and radiation, and setting the stage for the formation of the cosmic structures we see today. Inflation elegantly solves several problems in cosmology, such as why the universe appears so uniform on large scales and why it seems geometrically flat. But perhaps its most intriguing aspect is what it suggests about the larger cosmos. Many versions of inflation theory predict that our universe is just one bubble in a vast, perhaps infinite, multiverse. In this scenario, the process that created our universe is constantly occurring elsewhere, spawning new bubble universes with potentially different physical laws. If this is true, then our universe didn't have an absolute beginning. It's just one episode in an eternal process of cosmic creation. Indeed, the concept of inflation has led some theoretical physicists, like Andre Linde of Stanford University, to propose the idea of eternal inflation. In this framework, inflation never completely stops. While it has ended in our observable universe, allowing galaxies and stars to form, it continues in other regions, forever spawning new bubble universes. In this view, the multiverse as a whole has no beginning and no end. It simply exists, eternally inflating. Our universe, with its apparent beginning at the Big Bang, is merely a pocket of space where inflation happened to end, allowing for the formation of matter, stars, and eventually, curious beings like us who wonder about their origins. The eternal inflation scenario provides one possible answer to what came before our universe: an eternally inflating sea of space-time from which our universe bubbled forth. But it's not the only possibility that modern physics offers. Another approach comes from string theory, which attempts to unify all the fundamental forces of nature by suggesting that the basic constituents of reality are not point-like particles, but tiny, vibrating strings. The mathematics of string theory requires extra dimensions beyond the three spatial dimensions and one-time dimension we're familiar with. These extra dimensions might be curled up so small that we don't notice them in everyday life. But they could have played a crucial role in the universe's earliest moments. One of the most influential ideas to emerge from string theory is the Cyclic universe model, developed by Paul Steinhardt and Neil Turok. According to this model, our universe exists on a multidimensional membrane, or brane, which floats in a higher dimensional space along with other branes. Periodically, these branes collide with each other, and each collision appears, to those living on the branes, as a Big Bang. In this view, our universe goes through endless cycles of expansion, cooling, and eventual contraction, followed by another expansion. The Big Bang was not the beginning of everything, but merely the beginning of the current cycle. The cyclic universe model offers a radically different perspective on cosmic history. It suggests that time extends infinitely into the past and future, with no absolute beginning. Each cycle might last 1 trillion years or more, allowing stars and galaxies to form, planets to develop, and life to evolve. Eventually, as each cycle draws to a close, all structure would be wiped away in the contraction phase or the collision of branes, setting the stage for a new cycle to begin. If this model is correct, then the answer to what came before our universe is simple. Another universe, not fundamentally different from our own, just at a different stage in the great cosmic cycle. But there's a third approach that has gained significant attention in recent years: loop quantum cosmology, derived from loop quantum gravity, which is an attempt to apply quantum mechanics to the fabric of space-time itself. According to this theory, space is not infinitely divisible, but is made up of discrete quantum units, somewhat like pixels in a digital image. When these quantum aspects of gravity are applied to cosmology, they yield a surprising result. The Big Bang singularity disappears, replaced by a big bounce. In the big bounce scenario, our expanding universe was preceded by a contracting universe. As that previous universe contracted, it reached a maximum density. But instead of crushing down to an infinitely dense point, a singularity, Satanite, quantum-y, gravitational effects caused it to bounce back out, resulting in our expanding universe. Like a cosmic trampoline, the universe bounces from contraction to expansion and back again, with each cycle potentially lasting trillions of years. In this view, there was indeed a before to our universe. It was just an earlier phase of the same universe, contracting instead of expanding. What makes loop quantum cosmology particularly interesting is that it makes specific predictions that might be testable. For instance, it suggests that gravitational waves from the very early universe might carry imprints of the pre-bounce phase. Future gravitational wave detectors, either in space or on the far side of the moon where they're shielded from Earth's noise, might be able to detect these primordial ripples in space-time, giving us a direct window into what came before the Big Bang. And so we have three main theoretical frameworks: eternal inflation, the cyclic universe model, and loop quantum cosmology, each offering a different perspective on what might have preceded our observable universe. But there's a fourth approach that's emerging from the intersection of quantum mechanics and cosmology, and it challenges our very notion of time itself. According to some interpretations of quantum mechanics, particularly the no-boundary proposal, developed by Stephen Hawking and Jim Hartle in the 1980s, the very concept of a beginning to the universe might be misguided. In this view, asking what came before the Big Bang is like asking what's south of the South Pole. Just as the Earth's surface closes in on itself without a boundary at the South Pole, space-time might close in on itself without a boundary at the Big Bang. Time, as we understand it, simply emerges as the universe expands, much like how the concept of south emerges as you move away from the South Pole. The no-boundary proposal suggests that the early universe, rather than being a well-defined sequence of events unfolding in time, is better described as a quantum superposition of many possible geometries. As the universe expands and becomes more classical, this quantum fuzziness gives way to a clearer notion of time and cause and effect. In this view, the question of what came before might be fundamentally misplaced, not because time began at the Big Bang, but because time itself emerges from something more fundamental, a quantum reality where conventional notions of before and after don't apply. This idea reflects a profound shift in how physicists think about time. Rather than viewing time as a fundamental aspect of reality, many theoretical physicists now consider it an emergent property, something that arises from deeper quantum processes. In the words of the physicist Carlo Rovelli, time is not found in the fundamental equations that describe the world, just like temperature is not found in the fundamental equations of motions of molecules. We need to understand how time emerges. But, as compelling as these theoretical frameworks are, they remain speculative without experimental confirmation. Is there any hope of finding empirical evidence for what came before the Big Bang? Remarkably, there is. While we can't directly observe events before the Big Bang, we might be able to detect their traces in our universe today, like detectives, finding clues to a crime that happened long ago. One promising avenue comes from studying the cosmic microwave background, CMB, the remnant radiation from about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. The CMB acts as a cosmic baby picture, showing us the universe in its infancy. By analyzing subtle patterns in this radiation, Scientists have already confirmed many aspects of the Big Bang theory, but the CMB might hold even deeper secrets. For instance, if our universe collided with another brain in a cyclic universe scenario, or if it underwent a bounce as predicted by loop quantum cosmology, these events might have left distinctive patterns in the CMB. Scientists are particularly interested in finding signs of a special type of polarization in the CMB called B modes, which could provide evidence for gravitational waves generated in the universe's earliest moments. These primordial gravitational waves might carry information about what came before. Another possibility lies in the distribution of galaxies across the universe. The way galaxies are clustered together on the largest scales is influenced by quantum fluctuations that occurred in the earliest moments after the Big Bang. If our universe was preceded by a contracting phase or emerged from a previous cycle, these fluctuations might show subtle statistical features that deviate from the predictions of the standard Big Bang model. Advanced galaxy surveys, like the one being conducted by the Euclid Space Telescope launched in 2023, might be able to detect these deviations. Perhaps the most speculative possibility comes from the study of black holes. According to some theories, particularly those inspired by string theory, black holes might be connected to white holes, theoretical objects that, instead of pulling everything in like black holes, push everything out. If our universe emerged from a white hole in a larger cosmos, or if tiny black holes formed in the early universe can give us a window into pre-Big Bang physics, then studying these extreme objects might offer clues to what came before. But as we search for these clues, we should acknowledge the profound philosophical questions that accompany our scientific exploration. What does it even mean to ask what came before the universe? If time itself is a product of our universe, then the very concept of before might not apply in any conventional sense. As the physicist Julian Barber has argued, perhaps we should think of the universe not as a movie playing out in time, but as a vast collection of nows, individual moments that don't necessarily flow from one to the next in a linear fashion. This perspective echoes ancient philosophical traditions, from the timeless Brahman of Hindu cosmology to the eternal present of some Buddhist schools of thought. Perhaps what science is discovering through mathematics and observation has been intuited by philosophical and spiritual traditions for thousands of years. That our everyday experience of time as a linear flow from past to future is incomplete, a limited perspective of a deeper reality. Indeed, the question of the universe's origin inevitably touches on the boundary between science and philosophy, between what we can know through observation and what we might only be able to approach through reason or contemplation. The physicist Sean Carroll suggests that we should distinguish between different types of explanation here. There's the scientific explanation within our universe, how stars form, how galaxies evolve, how life emerged. And then there's the question of why there is a universe at all, with these particular laws of physics. The latter question might take us beyond what science can answer. And yet, despite these philosophical challenges, scientists continue to push the boundaries of what we can know about the universe's origin. New telescopes, like the James Webb Space Telescope, are peering farther back in time than ever before, observing the first galaxies that formed after the Big Bang. Advanced gravitational wave detectors are listening for the subtle ripples in space-time that might carry information from the universe's earliest moments. And theoretical physicists are developing ever more sophisticated mathematical models that might bridge the quantum and gravitational realms, finally allowing us to describe what happened at the very beginning, or before the beginning. The pursuit of these questions reflects something profound about human nature. We are the offspring of stars, assembled from elements forged in stellar furnaces and scattered across space by ancient supernovae. And yet, through our curiosity and intelligence, we've developed the capacity to trace our origins back to those very stars and beyond, to the earliest moments of the universe itself. In seeking to understand what came before the Big Bang, we're engaging in perhaps the grandest detective story imaginable, investigating our own cosmic ancestry, trying to piece together the events that led, through an incredible sequence of causes and effects spanning billions of years, to our existence on this pale blue dot. And so the question remains open. Did the universe have a before? The honest answer is that we don't know for certain. The standard Big Bang theory, which has been remarkably successful in explaining the universe's evolution, doesn't address what happened before the Planck time, that first infinitesimal fraction of a second. But newer theoretical frameworks, from eternal inflation to cyclic models to quantum bounce scenarios, offer tantalizing possibilities. Perhaps our universe is just one bubble in an eternal inflating multiverse. Perhaps it's one cycle in an endless sequence of expansions and contractions. Perhaps it emerged from a quantum bounce when a previous universe collapsed. Or perhaps time itself is emergent, and the concept of before doesn't apply in the way we typically imagine. What's certain is that we stand at an extraordinary moment in human history, where questions that were once the exclusive domain of philosophy and mythology are now being investigated with the tools of modern science. We're developing mathematical models that might describe what happened before the Big Bang, and designing experiments that might detect the echoes of those primordial events. The boundary between the knowable and the unknowable is shifting, and with it, our understanding of our place in the cosmos. For we are not just passive observers of the universe, we are participants in its story. Conscious beings emerged from its matter and energy, turning back to contemplate our origins. Through science, we extend our senses beyond their natural limits, peering across vast distances and back in time, closer and closer to the beginning, and perhaps, someday, beyond it. As we do so, we're writing a new creation story, one based not on myth or dogma, but on observation, reason, and the collective efforts of generations of scientists. This scientific creation story is still being written, its details refined with each new observation and theoretical breakthrough. But already it offers a perspective on our existence that is both humbling and exalting. Humbling because it reveals our physical insignificance in the vastness of cosmic time and space. Exalting because it shows how, through our curiosity and intelligence, we can comprehend the universe that gave rise to us, tracing our lineage back to the stars, to the primordial elements, and perhaps, someday, to what came before the Big Bang itself. And so the search continues, driven by that distinctly human blend of curiosity, wonder, and the desire to understand our place in the cosmos. Through powerful telescopes and sophisticated mathematics, through patient observation and bold theoretical leaps, we inch closer to answering one of the most profound questions we can ask. Where did everything come from? Did the universe have a beginning, or has it always existed in some form? Was there a before to the Big Bang, and if so, what was it like? The answers, when they come, might challenge our intuitions and transform our understanding of reality itself. They might reveal a universe far stranger and more wonderful than we've imagined. And in doing so, they'll write a new chapter in humanity's ongoing dialogue with the cosmos, a dialogue that began when our distant ancestors first looked up at the night sky and wondered about their place among the stars. Indeed, every culture throughout human history has crafted its own creation myths to explain how the world began. From the cosmic egg of Chinese mythology to the primordial waters of ancient Egypt, from the void of Norse legends to the divine breath of the Abrahamic traditions, humans have always sought to understand their origins. Today, that same impulse drives our scientific exploration, but with tools and methods our ancestors could scarcely have imagined. The telescopes scanning the distant cosmos, the particle accelerators probing the subatomic realm, the supercomputers modeling the universe's evolution. These are the modern equivalents of those ancient storytellers seeking to answer the same fundamental questions about where we came from and how it all began. And perhaps the most profound aspect of this scientific quest is that it's unfinished. The story of the universe's origin is still being written, with new chapters added as our understanding deepens. Each generation of scientists builds upon the work of those who came before, refining our cosmic narrative, bringing us closer to understanding what came before the Big Bang, if indeed there was a before in any meaningful sense. This open-ended nature of scientific inquiry stands in contrast to traditional creation myths, which typically present a complete and unchanging account. Science offers not certainty, but a method for approaching the truth, a method that acknowledges our limitations while constantly pushing against them. As we continue this quest, we might find that the question itself transforms. Perhaps asking what came before the Big Bang will prove to be like asking what's beyond the horizon, a question that changes as we move forward, revealing new vistas with each step. Or perhaps we'll discover that time and space themselves are more fluid, more malleable than we've imagined, requiring us to rethink our very notions of before and after. Whatever the case, the journey itself, this collective human endeavor to understand our deepest origins, is a remarkable testament to our species' capacity for wonder, reason, and the pursuit of knowledge. You've been watching the entire history of the universe. Don't forget to like and subscribe, and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.